Thank you. It is my great honor to be here to present our recent research progress on Spintronic terahertz emitter. Thank you, Tobias, for your invitation. My name is Xiaojun, and I come from Beihang University in Beijing, China. So since Tom has already given a lot of introduction about terahertz importance, I just go directly to the terahertz source. So previously, in the last 10 years, what we have done is to build strong field terahertz based on lithium niobate crystals. We have tried our best to use the femtosecond laser pulses, interact with lithium niobate crystal, and push the terahertz single pulse energy from the microjoule to millijoule, and then to tens of millijoule single pulse energy. And recently, we collaborate with Simon Cass by using the petawatt soft laser facility, and we get more than 20 millijoule terahertz out. So this kind of lithium niobate-based terahertz sources have a lot of applications. Maybe some people just use it for the nonlinear terahertz spectroscopy to study the spin waves, and so on. And what we use is this strong field terahertz to do electron acceleration. So we use the terahertz, strong field terahertz to interact with the electron and to build the compact X-ray sources. And recently, we use this kind of strong field terahertz to accelerate the electron, and we obtained the mega EV electron accelerator, but the size is very small. Why we use these two slides is just to give you, these years we use lithium niobate crystal to build a strong field terahertz source, but it has a lot of drawbacks, limitations. For example, the crystal is very expensive, and the tilted pulse front geometry is not as elegant. It is complex, and the pulse duration is long. The spectrum is not at broadband. So we need Spintronic terahertz emitters. And the second, people already know that the photoconductive antenna, which has the earliest commercial terahertz emitters and has been used in both in time domain and also in frequency domain terahertz spectrometers. But this kind of photoconductive antenna also have some limitations. For example, the bandwidth is limited, and the substrate, no matter it is gallium arsenide or indium gallium arsenide, and we need very expensive and bulky fabrication devices to build it. And for some spectroscopy application, also some imaging, what we use it. And we have to integrate a lot of photoconductive antenna together and to produce very huge beam, and so that we can use a single shot imaging to some specific applications. But this is also limitations for this photoconductive antenna. So these two kinds of terahertz sources, no matter it is based on the nonlinear crystal or the photoconductive antenna, they use the electron charge to generate terahertz, and Tom just has the, we can use spin to generate terahertz and also momentum to do that, right? So thanks to the demonstration of the Spintronic terahertz emitters, and we have the chance to get ultra broadband Spintronic terahertz emitter, and the bandwidth right now is already goes beyond more than 40 terahertz, and the field strength can even go to more than 1 megawatt per centimeter. So it gives us a lot of potential applications, both on the nonlinear spectroscopy, maybe also in the future for some electron acceleration and some other strong field terahertz biological effects. So what we have done in Beihang University these years is that based on this spin-to-charge conversion formula, and we change the non-magnetic metal to some topological insulators, and we try to optimize the spin whirl angle, and we try to manipulate the external magnetic fields, and we also try to enhance the spin-to-charge conversion efficiency. And what we do is, the first one increase the terahertz emission efficiency. The second one is whether we can just trace the terahertz at the source to fabricate some functional terahertz devices at the emitter. So for example, at the beginning, what we have done is we use the non-uniform magnetic field, external magnetic field, and we produce elliptically polarized terahertz beam directly at the Spintronic terahertz emitter. And then we also use the cascaded method to residue the the pump light, for example, the first emitter, they just absorb half of the pump energy, and we recycle the residue pump light, and then we use the phase difference between the first terahertz pulse and second pulse. We can produce a perfect circularly polarized terahertz beam by using this cascaded method. And these two methods are not so elegant. And recently what we demonstrate a more elegant one is that we directly coat these metals and by fabricate the metal surface on this one. So this is from the Tom's paper, and has already demonstrated that this Thomson covalent boron platinum tri-layers can give us very highly efficient terahertz radiation. So we directly choose these heterostructures with the optimal thickness. What we have done, we can see here is that if we only change the illumination facet, and then the phase, radiated terahertz phase, can directly give you 1 degree or 180 degree, and this one can even also be very broadband. So this gives us 0 and 1. That means 0 degree or 180 degree, and so that we can fabricate metal surface directly on this nanofilm. So this is the fabrication flow, and then first we can do the spin coating, and then we use the positive PR, and then we etch it, and then we sputtering, and then we etch it again, and then we use the negative PR and etch and sputtering. By doing this, we can fabricate this kind of grating patterns, and this is the design pattern, and this is the fabricated pattern, just to change different. One is the Thomson covalent boron platinum, and the other is platinum covalent boron Thomson. So why we do this is that we can get the beam splitting at the source, and this is the experimental test. So for this experiment, we have to use the tensor amplifier, and it divided into two beams, one directly illuminate on the sample, and the other for the direct imaging of these two spots. So this is the beam splitting demonstration, and we get a result at get the 10 degree diffraction 10 degree, and this diffraction angle 20 degree, and this is the experimental result, and the experimental result agrees very well with our theoretical design. Besides, we can just use this spintronic meter, and we can directly do the beam splitting. So we do not need another metal surface to do that. So it is very great. And the second is one, not only this beam splitting, we can also do beam focusing. Beam focusing means that we do not need lens, another terahertz lens to focus it. So this is the design pattern, the fabricated pattern, and so this is the calculated focused beam, and this is measured, and both also agrees very well. And also, the beam focusing, we can also produce vortex beam. So you may ask what vortex beam, and Tom has said, for the next wireless communication, for example, it can use a lot about that. So, and by using this one, and this is calculated, and this is measured, and so that we can use it. So what we just propose, just present this one is that I just want to say, since our workshop is spintronic terahertz devices, we can fabricate this metal surface on the spintronic emitter. We can get a lot functionalized spintronic terahertz emitters, and this one can, has many advantages. It's low cost, and we can code in these metals, and the damage threshold is also high. Can work in the kilohertz and the megahertz system. For the experimental demonstration measurement, we just use kilohertz, but it definitely works in the megahertz system. And all this works, we have to use the external magnetic field. So the other thing is that since what I was doing in the last 10 years to generate strong field terahertz, and I'm always thinking that if we use a 4-inch and we extend the beam size, and we can also get strong field terahertz. How about 8-inch? and we get even more large facility lasers through SDR. We just directly change the vacuum chamber, the window of the vacuum chamber, and then we can get the terahertz spin out, and also you can use the residual femtosecond laser because the residual laser pump, the pump spectrum did not change, but lithium niobate cannot do that. So if we just enlarge the Spintronic terahertz the size, there may be a lot of problem comes. The magnetic field distribution may not touch uniform there. So can we just try to find a solution not to use the external magnetic field? So this is the main topic is that there is a normal, you are expert in the magnetism, I mean not that one, but there is an exchange burst effect, we call it spin pinning effect. We can directly attach a FM on the FM, and then the FM will try to spin pinning the FM, and so that we do not need the external magnetic field, we can directly magnetize the ferromagnetically. So to demonstrate this idea, we choose the iridium magnetizing to attach on the carbon iron boron. It's carbon iron boron, and the optimized thickness here, we choose 2 nanometer and 2 nanometer. And so this one, we do not use the external magnetic field. And to verify this is spin to charge conversion or inverse spin Hall effect. And we can do 2 things. One is up and down flip. So if the spin current in this direction and then flip, up and down flip, so the radiated terahertz phase will not change. However, if we rotate this one, left and right rotate, the spin current changes side. So the terahertz phase will change. So that is a very easy way to check this spin pinning effect. And other things that we try to further confirm the mechanism, and we add external magnetic field. So the interesting thing is that if we add external magnetism here, and then the spintronic just become to the conventional spintronic, like the platinum, carbon iron boron, the Thomson, and then we check it, and then we should use the normal instance. We just change the magnetic field direction, and then the terahertz radiation phase, change this. And the more interesting thing is that we just get rid of the magnetism and then only the spin pinning effect. So first the spin pinning in this direction, and the external magnetic direction in this thing, and when we get rid of it, so the spin pinning just predominant the terahertz radiation mechanism. So it is an immediate process. So other thing is that everyone can think about this idea. If we want to recycle the backward flow terahertz, the spin current, and we can further enhance the radiated terahertz. So we compared this one with the conventional platinum, carbon iron boron. This is Thomson, and in our case it is comparable. So the radiate efficiency. And also, previously Tom said that if we want to manipulate or tune the radiated terahertz polarization, we can rotate the external magnetic field. And so in this case, we do not need to rotate we don't have the external magnetic field. So how can we change the polarization? We directly change the sample. So just like the emitter, just like a half-wave plate. So we rotate the sample azimuths, and we get different radiation. And we also have done some preliminary results to verify our this one can be used to generate high field terahertz. So we fabricate 4-inch sample, and we use the laser amplifier to directly illuminate on this sample, and we compared it in this is in air, and this is nitrogen purged, and this is from the lithium niobate. So under the thin pump laser parameters, and the radiated terahertz fields in our case can goes around 100 kilovolt per centimeter. Is comparable to the lithium niobate, but still smaller than that. Yeah. But I think if we further optimize this, as it may have the chance, just like what you have done in the physical review applied, and we can design some resilient structures and to further enhance the radiated terahertz electric field strength. So, to our small conclusion for this one is that we have demonstrated a spintronic terahertz emitter based on the antiferromagnetic and the ferromagnetic heterostructures, but without external magnetic field. So we see the potential application for that is we can use this one for the 4-inch or even 8-inch without magnetic fields and for some single-shot imaging. And we do not need to scan. Just use the photoconductive antenna, and it may also have the chance to get very strong field terahertz for extreme terahertz science and applications in the future. And the other thing is that for this one, we do not need the field, and recently we demonstrated another work whether we can use this method to the 2D magnetic materials. So why 2D magnetic materials? Because it's a 2D magnetic material have a lot of potential applications in spintronics. But the main point here is that when we just thin these magnetic materials and due to the thermal fluctuation, it cannot keep the long-range magnetism at room temperature. So people are trying their best to fabricate this kind of, to produce this kind of 2D materials that can work at room temperature. There is one possible way is that we directly attach the topological insulator onto the 2D material. And then this one is we could choose this iron, germanium, titanium. And here, the topological insulator bismuth telluride, they have two functions. The first one is it can induce this guy to have the room temperature magnetism. The second one is that it offers us very, very large spin Hall angle. So it means if we use this kind of heterostructures and we illuminate on this heterostructure, we can also have the chance of get terahertz. So the result is shown here, and this is the signal from the heterostructure. This is from the topological insulator. There is no terahertz from the pure iron, germanium, titanium. And so here we have something from the topological insulator. We have to get rid of it. So the first thing we do is that we can do the pump laser polarization dependent on the terahertz steps. And you can find the periodic signal here. So that is from the topological insulator. And the second method is that we can change the illumination facet, and then we can verify that it is a spin-to-charge conversion effect. And then for this one, we have to use the external magnetic field. And then when we rotate the magnetic field, we get this with very perfect symmetry distribution. So do this kind of measurement, we verify it is spin-to-charge conversion effect, and to extract the spin-to-charge conversion component, and we directly just use the linear polarized illuminate on bismuth telluride, and we can extract the SCC component and get rid of the component from the topological insulator. So, and we can, at the room temperature, we get terahertz. But if we further cryogenic cooling this sample by the liquid nitrogen, and the magnetism of this 2D magnetic material will be enhanced. So plus the topological insulator assists the terahertz radiation to room temperature, and then the cryogenic cooling one can also enhance the magnetization. So you can expect that the terahertz radiation intensity will be enhanced at low temperature. And also you can just attach the Thompson on this guy, and you can get some enhanced terahertz radiation. So that is why we choose 2D materials for terahertz. But the question is here that whether we can attach directly the kind of antiferromagnetic on the 2D material to directly induce it to room temperature and without Yeah. So we cannot find the area magnetized as a kind of antiferromagnetic to directly attach on this FGT. And what we found here is a chromium antimony. This kind of chromium antimony can be together with iron germanium titanium to be a superlattice, and it has verified in this article that if you fabricate this as a superlattice, you may have the chance to increase the Curie temperature of the FGT from 140 Kelvin to 200 Kelvin. But it doesn't mean we have the chance to get room temperature terahertz radiation. So what we observed here, interesting thing is that we observed terahertz radiation at room temperature, and there is a very small signal from the chromium antimony. Yeah, so why we can observe terahertz at room temperature from this superlattice without external magnetism? And to further find this mechanism, yeah, what we do the routine work is that we change the azimuth, the sample azimuth angle, change the pump laser polarization, and we try to extract the SCC component, and we do this kind of things. We can verify that this terahertz radiation mechanism is definitely spin to charge conversion. But the key problem here is that why it can be happening at room temperature, because, so here we propose that there may be some ultra-fast magnetization process happened in this superlattice. So previously, Tom said that we use the ultra-fast demagnetization as the electron dipole to radiate the terahertz. But for this one, it can only happen at low temperature, but we observed the terahertz radiation at room temperature without magnets. So, and to verify that, so for this comparison, we only have one thing, is that we use femtosecond laser pulses, and it gives us very low energy at megahertz distance. And here we use the time-resolved marker to also do it. We use 8 nanometer pump and 400 probe, and we also observed the room temperature magnetism. So we think that it is femtosecond laser-induced magnetism at room temperature. To further verify that, we also have done the VSM measurement, and there is no in-plane magnetization if we don't have femtosecond laser pulse illuminated on that. And we found some theoretical collaborations and from the IOP CAS, and they just give us some theoretical exploration, said that when we have the femtosecond laser illuminated on the superlattice, and it has the chance to short the atom distance between them 0.1 nanometer. Because of this shorter distance, and enhance the exchange bias effect. So only that one, and just push the Curie temperature around 200 Kelvin to room temperature. But there are still a lot of questions there. So whether it is direct, the mechanism ultra-fast magnetization, or somebody just said maybe there are some residual ultra-fast demagnetization. We have to add more experiment on that. And the other thing is that what is the radiation mechanism from this chromium antimony antiferromagnetism? Does it only the influence like the topological insulator, or are there some spin current induced also inside this AFM? So other open questions, both this kind of mechanism can, and the topological insulator can just combine in one. Maybe we can find only one material and both can play the 2 roles, and some other ultra-fast magnetism, other 2D ferromagnetic AFM. So that is the all my talk. And finally, I'd like to thank my previous PhD student and Xiaojun for this FGT and topological inserted work. And the second one is AFM and FM without field. It's from my Groningen scientist collaborate with me, and the final work is from my PhD student Beihang Chen. And these Groningens just fabricate some materials and the structures for us. And with this, I'd like to thank all of you for your attention.